right, welcome back, everyone. So our main symposium for the annual meeting is on the trustworthiness of science. And I'm going to spend just a few minutes talking about the background for why we chose this topic. So I want to begin with the hierarchy of trust in science, because when we talk about trust, we don't always distinguish between what parts of science we actually trust. And I think that as scientists, we all absolutely trust the scientific method and consider the method the most foundational part of science. And the method being that we clearly state our hypotheses, we test them with evidence, we expose our work to critical review, we share those results, show our data, we're skeptical of our own results, and we avoid bias. In other words, the results of whatever we do should be independent of who did it. And this sort of encapsulates what is the scientific method, and we as scientists all buy into this as the essential way that we do our work. And so this is something we all agree on as a trusted approach. And then the next element of science is what I'll call the consensus. While we absolutely trust the method, we have a lot of trust in the consensus. It's the most trusted form of finding, but it's nevertheless subject to occasional revision. So we trust it only so far. We recognize that it can be revised. And so, for example, I put up here the plate tectonic paradigm. It's been around for, 50 years or so, and we trust that it is on pretty solid ground, but I'm not going to say that it will never be overturned, but the fact that it survived for 50 years, it's probably on pretty solid grounds. And then in terms of the scientific hierarchy, what I'd say we have the least trust in is an individual study. It's only a candidate for scientific truth, and it's got to earn trust. So I have created here this little meme for sort of this hierarchy of trust in terms of this giant Jenga game. Now, for any of you who have ever played Jenga, you know that you create this tower of blocks and you try to pull them out one at a time and keep it balanced. And I put at the bottom of it the scientific method, which is the foundation. It's a solid foundation. We all trust that that foundation is rock solid. And the scientific consensus is the top of the tower, and it rests on a whole bunch of individual blocks, which are the studies. And so we trust that the scientific consensus is the product of all those studies, and we believe in the scientific consensus. But if too many of those individual studies are pulled out and proven to be wrong, eventually the scientific consensus will tumble. And if that happens, we call that a paradigm shift. And we have to build a new tower with a new scientific consensus based on new studies. And so, we have to erect a new consensus. So, as I say, individual studies have to earn trust. They have to work together to build a consensus, and this is my kind of meme for it. Now, if we look back at how we establish trust in the good old days of the past. When I was a student or an early career researcher, we might ask the following questions. Was the work published in a peer-reviewed journal? Was the work published in a peer-reviewed journal with really high standards? Or we might ask, do the authors have a reputation for excellent, careful, quality-controlled research? And those are the kinds of things we might have asked ourselves back in the 1970s or so. But then the research enterprise got really big. And suddenly it wasn't possible to know the reputations of all authors because the enterprise was so large. And more papers were interdisciplinary and international. Even as an author, it wasn't possible to check the results of all your co-authors who were in fields very different from your own. If you were a biochemist, you couldn't check the results of the geneticist who was working with you. And if papers were international, you didn't know the ethics or the culture of co-authors who may be from different cultures. And in addition to that, the stakes got high. Science became very important for the health, for the economy, for the environment, for quality of life. The results of scientific research were not just of academic interest. It became big business. So the simple rubric of, was it published in a peer-reviewed journal and did you know the reputation of the person, that wasn't working anymore. So as a result, and then in addition, there got to be very diverse channels of dissemination. Increase in number of journals of variable and sometimes unknown quality that were needed to handle more than 2.5 million papers per year. There were preprint servers, predatory journals became suddenly an issue. And many journals, we didn't know whether some knowingly didn't have peer review and some had unknown peer review. So the response of the scientific community was to develop new methods for transparency and reproducibility, asking questions like, are the data, the materials, the computer code, the methods available for independent scrutiny? Have the authors declared all sources of financial support and real or apparent conflicts of interest? Are the findings and conclusions adequately resolved by the experiment design, by the data, and are they based on appropriate use of statistics? And have the results been independently replicated, or have they been confirmed by other means, other blocks in that Jenga tower? So all of this is sort of directed at the scientific community, but not necessarily is all of this the most important things for communicating with the public of the trust in individual studies. So I contrast here the two worlds, science as practiced and perhaps what the public is expecting. For example, for science as practiced, we view that a study is worth publishing if it's a major advancement on or an overturn of accepted scientific views. We want to be original. We want to be different. We want to be pushing the frontiers. But yet the public wants to see consistent messaging because that reduces confusion. Many have been taught that science is an eternal body of facts, and they get very confused when they see red wine is good for you. No, red wine is bad for you. Maybe it's good for you, maybe it's not. And science is practiced. Remember, one of the tenets of the scientific method is that the results should be independent of who practiced it. Whereas the public wants to see that scientists and their stories are important, They don't want to see this dispassionate, cold, impartial scientist. They want to see a real person behind it who actually is, caring about the results and the people that are impacted by it. And science is practiced. All caveats and uncertainty should be included, whereas uncertainty makes the public think that scientists actually don't even know what they're doing. So all of these are problems, and let me just leave you with this. What will be the future of trust? Well, I hope that scientists will learn to communicate better with non-scientists, reaching their hearts and souls, not just their minds. We as scientists talk to each other, mind to mind, but in talking to the public, we really need to reach their hearts and souls. And I hope that non-scientists will better understand that science is not just a list of facts, but an ordered way of seeking the laws of the natural world. And I hope that scientists will become more professional at signaling what they trust and what they no longer trust or perhaps never trusted. We don't do a very good job of that signaling. We implicitly know it within our community, but we don't do a good job of signaling it to not scientists. And I hope that non-scientists will become more savvy consumers of scientific information and distinguish consensus from single studies. So now I'd like to hand this over to Kathleen Hall Jamieson from the Annenberg School, who's going to give a teaser of her keynote and introduce you to a poll. All of you have these on your seats. You may think they were mute buttons to turn me off. They aren't. They are going to be used for some voting and fun things. We're trying to be very innovative in this session and get you engaged in it. So, Kathleen.
Thank you. You are now becoming an official part of our symposium by providing us with data that tells us what the perception in this room is of these important questions. And now when I advance, we should be seeing something that says, this is how you're going to use your remote controls. This is an NAS audience poll from the members of this room, and it generalizes to nothing beyond this room, and not even to this room, because we're not sure all of you have the handheld devices. There'll be a series of questions. Each question will be read aloud. You'll have 10 seconds to answer each question. Using your keypad, you can enter your response when the question is displayed. You don't have to wait for the countdown clock. Using the keypad, press the button that corresponds with your answer. The keypad will accept your last answer. The response period ends once the countdown clock has expired. And now we're going to switch. Question 1. Thinking about scientists in general, to what extent would you say that scientists in general are competent at what they do? We're using a scale from 1 to 5, where 1 means hardly competent at all, and 5 means very competent, competent to a great extent. Of course, you may use any number in between. We are pleased that the scientists in the room have a high sense of competence. Next question. Thinking about scientists in general, to what extent would you say that scientists in general are honest and trustworthy? Same scale, 1 to 5. 1 means scientists in general are hardly honest and trustworthy at all, and 5 means scientists in general are very honest and trustworthy. Please vote. Next question. How much does it matter to you when deciding whether to believe a scientific finding? When the scientists make their data and methods available and are completely transparent about their methods, does that matter to you when deciding whether to believe a scientific finding? Does not matter as 1, matters a great deal as 5. Start the clock. Next question. How much does it matter to you that the scientists involved in the study show their openness to changing their minds based on new evidence? This is in assessing a new finding. Does it matter not at all, or does it matter a great deal? And next question. How much does it matter in assessing a finding that the scientists involved in the study disclosed the individuals and the organizations that funded their work? Next question. In general, how confident are you that scientists provide the public with trustworthy information about the science in their area of inquiry? Are you very confident, somewhat confident, not too confident, or not confident at all? This is a 1 to 4 scale. Please vote. And what we're going to do at the break is compare your answers to those of a national probability sample. Let me then step back and try to put this broad area of inquiry in context. Across time, we know that confidence in the leaders of the scientific community has been stable, or largely stable. This is Pew data. We also know that Americans' trust in military and scientists remains relatively high, but there's lower trust in media, business leaders, and elected officials. This is again Pew data. But we're also facing a situation in which there's a lot of information being moved into the public now that says that science is facing challenges. And the existing survey research hasn't addressed whether the public perceives these as challenges or how it perceives potentially their relationship to science, scientific inquiry, and scientists. And so we created for this symposium a poll, a survey, a national probability sample of 1,253 individuals interviewed in January and February. Margin of error, 3.4 roughly. Here are some of the things that we found. Perception of scientists' competence exceeds their trustworthiness, which exceeds the sense that they share values. And that's share my values. These are 3 traditional indicators that taken together are used to assess credibility of institutions or trustworthiness of institutions. Notice that we asked you about 2 of those 3 in the preliminary poll. But overall, the public is confident that scientists do provide trustworthy information. Note the 74% falling over to the positive end of the scale, very or somewhat confident. We also see that public's confidence about scientists that they offer unbiased conclusions about their work varies somewhat by field. But nonetheless, these percents remain relatively high compared to those you'd expect in other institutions. But partisan differences do exist. Genetics includes genome and related areas. While cancer research is frequently recalled in an open-ended question asking about the major discoveries you remember from the last decade, and it's remembered across parties as an important discovery, you see a difference in what's recalled, with Democrats also featuring climate-related findings. A majority believes or sees scientists as neither liberal nor conservative, but 33% say liberal and 9% say conservative when asked their impression of the ideology of scientists. And a plurality believes scientists can overcome their biases, but 39% is a somewhat worrisome figure there. There are other worrisome indicators. This is the perception of frequency with which replication fails when an independent other group does the replication. We don't know whether that 24% represents an accurate assessment of how often replication fails or not. Worrisome indicator, perception of frequency of fraud in scientific research. This is just your best guess. How often does fraud occur in scientific research? 28% say it occurs often. Another worrisome indicator, how often does a scientist exaggerate the significance of a study's findings? 34% says often. Worrisome indicator, perception that scientists do whatever it takes to get grants and publish, even if that means cutting corners. 50% agree. Worrisome indicator, will scientists publish findings that run counter to the interests of the funding organization? 59% think that when they run counter, the findings will be suppressed. Nonetheless, we have some good news. The percent of the public somewhat or very familiar with the National Academies of Sciences, Engineering, and Medicine is 41%. But a higher percent that is familiar says that they trust the National Academy of Sciences and Engineering and Medicine when it comes to climate and climate science. Notice the difference across these groups, and notice the Intergovernmental Panel on Climate Change, which has been highly politicized as a result of attacks on its integrity, is falling into a lower category. Yet, consistent with high trust, most consider science a reliable way of knowing, 88%, and believe that science is more reliable now than it was 2 decades ago, 61% more reliable. So thank you to all of you who increased the perception that science is reliable as a way of knowing, and we now turn to our first panel.
Pleasure. Is this? Oh, yeah. Okay. My pleasure to introduce the first panel. So, first speaking will be Susan Fiske, who's the Eugene Higgins Professor of Psychology and Public Affairs at Princeton. She got her PhD from Harvard, and she investigates social cognition, especially cognitive stereotypes and emotional prejudices at cultural, interpersonal, and neuroscientific levels. She's sponsored by Guggenheim for her Russell Sage Foundation book called Envy Up, Scorn Down, How Status Divides Us. And she's the author of about 400 publications and a winner of numerous scientific awards. She's a member of the National Academy. Speaking next will be David Dunning, who's a professor at the University of Michigan. He's a social psychologist focusing primarily on the psychology underlying human misbelief. His most cited work shows that people hold flattering opinions of their character and competence that cannot be justified from objective evidence. He's the author of over 150 journal articles, book chapters, and general interest pieces. He's half of the team responsible for describing the infamous Dunning-Kruger effect, in which ignorance fails to recognize itself. He has served as president of both the Society of Experimental Social Psychology and the Society for the Science of Motivation. In 2016, he was awarded the Distinguished Lifetime Career Award from the International Society for Self and Identity, and has been a fellow of the Center for Advanced Studies in the Behavioral Sciences. He got his PhD from Stanford. And finally, Margaret Levi is the Sarah Miller McLuhan Director of the Center for Advanced Study in the Behavioral Sciences at Stanford. She's the Jerry Ill Barak Professor Emerita of International Studies in the Department of Political Science at the University of Washington. She was a Guggenheim Fellow and has been elected to the American Academy of Arts and Sciences and also the National Academy of Sciences and the American Academy of Political and Social Sciences and the American Philosophical Society. She served as president of the American Political Science Association in 2004 to 5. She has numerous awards and was awarded a prize for having laid the foundations for our understanding of why citizens accept state coercion by combining theoretical acumen and historical knowledge. So, Susan, lead us off.
I realize that the clicker is at the podium, so.
Oh, yes, right.
So much
Sorry,
for the talk show
We need the
format.
clicker. Yes.
What I'd like to talk to you about is the work that we do on how people form impressions of individual people, but focus it on scientists, and so we can examine our reputation together. So what's at stake, of course, is trust in us as scientists. We'll be talking about different levels of analysis on this panel. Trust is really crucial in any kind of interpersonal judgment, and it's also adaptive. It makes people more efficient, but it's very relative to different situations and different kinds of comparisons, and it's fragile. Communicator credibility requires trust. There are two components in research on communicator credibility. The first one is expertise, knowledge and the ability to be accurate. But the second one is trust, and that's interpreted as the person's intention to be truthful. So the image that we have as scientists depends crucially on trust. And what we find is that people want to know whether we're on their side or not. If we're totally self-interested and just worried about our own funding, then we're not on their side. If we're trying to do science for the good of the country and the good of humankind, then we're more trustworthy. The competence dimension is whether we're able to act on that. So what I'm going to talk to you about are those two dimensions, which are part of the reason that they were in Kathleen's survey. This space, this warmth by competence space for making sense of people or groups of scientists, for example, is universal. I use that in quotes with an asterisk by it. Of course, nothing is universal, but this comes pretty close. It's been shown to work as a dimensional breakdown of understanding social cognition across cultures, 50 different countries over time and groups. Let me give you where we stand. So if you look at this, you can see that the vertical axis is warmth, which is trustworthiness, and the horizontal axis is competence. So you can see if you look at scientists that we do pretty well. We're seen as highly competent, and I've put us in red in various guises that we might be seen as a teacher or a professor or a researcher or a scientist. We're sort of middling on trustworthiness. So I think that we saw that there were some worrisome trends in the data that Kathleen was showing. But my point is, relative to other groups, we're way out there on competence. And so people believe in that part of our image. You can see other kinds of groups are seen in other ways. So in our data, at least, the trust is kind of neutral. And the question is, why? We have the competence. So the middling form of trust, is that indifference to our trustworthiness, or is it a relative deficit, or is it just sort of missing information that people have? So here's what people mention frequently when you ask them to describe scientists. You might notice that there's a lot about competence and not anything about trust. These are things that are distinctive to scientists. So again, it seems like most of what people think about when they think about scientists are competence and curiosity and intelligence, but not so much about whether we're trustworthy or not. This is a different kind of chart than one I showed you before, but basically it makes the point that the relevance of the two dimensions in open-ended descriptions, scientists and engineers are way out there on the relevance of competence, but the relevance of trust and warmth is kind of low. It's just not seen as a big deal. But I want to argue that we should pay attention to trust. It's fragile. The operating characteristics of trust and competence are different. And even though this is not salient in our image and not what comes to mind, the innuendos that people could make about our trustworthiness are problematic, and if it's sort of absent in our impressions of us, then it could be easily manipulated to make us seem untrustworthy. So here's the different operating characteristics of competence and trust. If you are a genius, you can do something really stupid, and you're still a genius. You know, the absent-minded professor, for example. So competence is solid when one violation doesn't destroy it. But on the other hand, with trust, if you're trustworthy and you do something to betray that trust and you're seen to be corrupt or dishonest, the recovery is very slow. It's hard to do. So the operating characteristics of competence and trust are quite different. So what I want to argue is that even though it's not a huge portion of people's current images of scientists, that we have to watch out for it because it's fragile and hard to recover. Okay, so I would argue in answer to the question, much is at stake in impressions of scientists, and we should pay attention to it.
I'll be right here. Wait for the screen to come up. Maybe. Excellent. I'm going to be continuing talking. You're going to start to see different themes start to echo because the work that we've been doing in our lab and the story I'm about to tell today does echo things that Dr. McNutt and Dr. Fiske have been talking about. In our work, what we're interested in is when does the general public trust or distrust scientists when it comes to contentious issues? And they're certainly out there. We have vaccines currently being a preeminent issue. We have climate change always being a preeminent issue. And the question becomes, why should the general public trust us? What's our superpower that makes us, in our opinions, more worthy of an audience than potentially other people's? Especially when you think about what people tend to think about, what they understand about scientific evidence and scientific conclusions. Our work starts out with the work of Andrew Schulman, who basically went out and asked Harvard students and Occidental College students in LA why they believed in such scientific concepts as oxygen, for example, or an electron, for example. Never seen one. What leads you to believe that they actually exist? And what's interesting is that often people's answers rest on, well, that's what my teachers told me, that's what my parents says, that's what everybody says. And if you take a look at people's answers, you realize two things. The first point is Andrew's, is that's what people also say about supernatural concepts. Like, why do they believe in ghosts? Why do they believe in karma? Heaven, for example. It's what other people say. It's what the authorities say. It's what consensus, social consensus, is around me. So in some sense, in people's heads, when you ask them for the epistemic base of why they believe in scientific concepts, the epistemic base is often quite similar to the epistemic base they have for the supernatural. That's number one, but that's not the important observation today. What people don't say is they don't talk about data. They don't talk about observation. They don't talk about the scientific method. They don't talk about crucial experiments. Rather, they talk about what people say. They don't talk about what we tend to spend our day doing to reach conclusions or to substantiate the theories that we ultimately come to favor. People don't talk about scientific rigor. They don't talk about scientific method. They don't talk about the constraints we have to defeat or at least use to test our ideas before we can put those ideas out there. And if you think about that, you can then start to ask, well, what do people think is our relationship to data and to the scientific method? That is, what do they think is going on? Well, that's been an issue that we have been surveying for the last 2 years in terms of if you don't think of scientific rigor and data as a constraint on what scientists can say, what do you think it is? And it turns out that not a majority, but a good plurality of people actually tend to think, if they think of data at all, if they tend to think about the empirical method at all. What they tend to say is that data comes after the fact, that essentially scientists are quite free to reach the conclusions they want to reach, and then data comes in as an illustration or an ornamentation to conclusions already reached. That's not a majority view, but that's a view that's certainly that one sees out there. And in some sense, what it really reflects, and what I want to argue today, is that when people think of science, they don't necessarily think of the empirical part of what we do and the authority that we give to data and to the rules we live under in the collection of that data, finally leading to conclusions that we can make. Now that matters, because if you survey people and they suggest a view that they believe scientists can say whatever they want, that they're not constrained by data or the rules of data collection, that does have quite a big relationship with trust of scientists, both in terms of the motives that scientists may harbor and also of the expertise that scientists might have. To the extent that people think scientists can say whatever they want to say, people have less trust on both of the important dimensions that Susan mentioned. Which leads to a second question. What seems to be behind this opinion that scientists can say whatever they want to say? Well, what we've been looking at is we've been looking at to what extent do people know how much data and scientific rigor and the scientific method actually does present a constraint on what we can say. So what we've been doing is giving people a quick test, an 11-item test, on to what extent they can spot constraints in terms of what scientists can say. We'll give them a scientific scenario. The scenario might have a problem in it, and the question is, can people spot problems that will prevent that scientist from making the conclusion that they can make? Do people, for example, spot that the person didn't have a control condition, or didn't randomly assign, or assume causation when they only had correlation, or cherry-picked results? Do they see that there are these violations of the scientific method there that would prevent the person from being able to make the claims that they're trying to make? And that matters, because to the extent that people think the scenarios are just fine and don't present any barriers, don't present any issues, they're much more likely to say that scientists can say whatever they want to say. In fact, the correlation is 0.6. That is, the extent that people fail to see the constraints on what the scientists can say in this particular scenario, the more likely they are to say that scientists can say whatever they want to say, leading to, in some sense, a nice psychological model, if you will, that knowledge of scientific rigor is necessary to cause people to understand that, well, scientists just can't say what they want to say. And once people have that in mind, they're much more likely to trust. Now, towards that end, what we've been doing recently is we've been trying to see is if we actually introduce people once again, or perhaps reintroduce people to the idea of scientific rigor, that there are hurdles, that there are standards, that there are issues that can disqualify a scientist from being able to make the claims that they want to make. Does that cause people to have more trust in what scientists have to say, to set aside any suspicions they might have for the motives and the competence of the scientists? So we've developed an interactive module that we use to train people on the internet to introduce them to ideas about unique control conditions, that your hypothesis has to be falsifiable, and so on. We introduce or reintroduce or introduce people to the idea of peer review and the fact that work does get rejected from professional journals, so that they understand that there are constraints on what we can say. Many of actually the elements that we have in the intervention addresses principles that Dr. McNutt actually introduced in her preliminary remarks. There are a few things you said that we don't say, and I would like to steal them for any revision. Thank you. And it turns out that that matters in the sense that if we bring to people or make more salient to people the idea of the scientific method, scientific rigor, the authority of data, the constraints that we all live under, that does significantly reduce the opinion that scientists are able to say anything. Doesn't do anything about trust in scientists as experts. We have that. But it does cause greater trust in the motives of scientists, and as well causes more trust in science as a collective effort. That there's an understanding that collective or discipline standards have to be met, not just the standards of the individual scientist. Just to bring this to a point and an end, is that in some sense, one of the potential sources in the general public for distrust that we might be facing is that people don't bring to mind the idea of the constraints that we live under in terms of what we have to do in order to come to some sort of conclusion, and then to publish that conclusion in a scientific professional journal. That's not to blame people. That might be an issue in education. That might be an issue in terms of when science gets talked about, what gets talked about. Is it the products of the science or the process of the science that gets talked about? But it does suggest something that we can potentially point to or heighten more that might bring about more trust in the general public, is just noting just some days how hard our job is. I'll end there.
Thank you. I'm waiting for mine to come up, but I'll start. So I was reading The Atlantic yesterday, and there's a very interesting article about the overtreatment by dentists. And the reason I'm bringing that up was part of the problem, and it was serious overtreatment, is that there's not good evidence-based dentistry. That's a problem. But there's also a lack of information among the public about what constitutes appropriate dentistry practice. Now, the culprits were caught by other dentists, and they were punished professionally, and they were even taken into courts of law. But the effect of it, as one of the patient victims said, was he damaged the trust I need to have in the people who take care of me. So what I want to talk about today in my very short time is the institutions. Be talking about personal knowledge, understanding of trust, interactional understanding of trust. And I really want to talk about the institutions that need to be put in place in order to increase the trustworthiness of science. And by institutions, I mean the norms, the rules, and the actual laws that might be needed to do that will affect the actual trustworthiness of science and the public's perception of it. I'm a comparative political economist, as you heard, who studies the relationships between governments and other organizations, such as labor unions, and those they are meant to serve. So my data is a little different than the kind of data that you've heard expressed so far. I look in detail at a variety of historical cases. I compare them. I formally model them. I derive testable implications. And then I test, or my collaborators and I test, with a variety of tools that go from surveys and behavioral tests of various kinds. But we're looking often at historical material or material elsewhere, so it's a little different kind of approach. So what I've put up here is what I've derived over time from a variety of studies about the virtuous circle of government and governance more generally. So if we can begin to establish something approaching a trustworthy government, what I want to argue that it then leads to a perception that the government is legitimate, that it should be asking for extractive demands of various kinds, which then creates behavioral legitimacy, that is compliance, or voluntary compliance or some quasi-voluntary compliance, which then leads back to enhancing the government's trustworthiness. In the case of government, that has to do with some things that are obviously specific to government and different than science. But one of the things that I want to emphasize here that links with what has already been said by Susan, by Marcia, even to some extent by David, is the importance of competence and the perception of administrative competence, and also the importance of fairness. And by that, I mean not just the due process by which we arbitrate, but also the fact that who's ever regulating this governance system is able to monitor and to find and locate and ultimately punish the wrongdoers. So that those of us who want to comply with the norms, the rules, the laws, feel that we can do so without being suckers, that the free riders and the actual violators of laws will be caught. One other thing I should add is that my definition of what counts as trustworthy is very related to what you've heard, but I want to add one other piece of it. And I think this is very important in thinking about science, which is that part of what it means to be trustworthy as a scientist is that the public or others believe that you have the public's interest at heart. It's not just issues of being felt to be honest, to be felt to be warm. All of those things matter, but it also, there has to be a belief that's often supported by institutional arrangements that you have the interest of others that you're supposedly serving at heart. Now, what this slide does is just reiterate some of what you've already heard and tries to put it into some kind of form that I could then play with. So these are the various factors affecting scientific integrity. And Marcia really covered almost all of these. I, again, am just emphasizing here that it's not just the motivations that we have as scientists for discovery and advance. It's also making sure that our incentives are in line with that, and the incentives that we have are reputational, getting promotions and recognition, getting funding, but that there's also some mechanism in that process for monitoring and punishing the wrongdoers or embarrassing them, removing their funding, something. And that all leads to scientific integrity. What undermines scientific integrity are when there are obvious examples not only of inconsistent science, that's one thing that can affect that, but conflicts of interest, which then change the incentives. And corporate science and big science, as we've heard, can have some of that consequence. This is just another way of putting that same kind of thing if we want to think about public perceptions of trustworthiness. Again, a number of the things that we've already talked about contribute to that. What can encourage trustworthiness in science or produce it are, again, a number of things we've heard about. University and professional association monitoring and punishment, the requirements of reproducibility and transparency. And one of the interesting ideas I think is worth exploring further is the suggestion that you and others made, Marcia, about a regulatory research board. Let me come back to that. So again, another way of putting these issues, if we really want to, and this is trying to get at the institutional dimensions of it and how we really introduce the institutions, is that we want to have some kind of, and this reiterates in a way my trustworthy governance virtuous circle, if we need to create some kind of effective regulatory apparatus, and we have much of that. And by regulatory, I don't just mean big government coming in and making laws. I mean our self-regulatory mechanisms, which come with the norms that science introduces and produces in us, with our professional oversight and processes, which are also increasing regulative procedures, and of course with other oversight bodies as needed, and they are at times, as we know, needed. These regulatory mechanisms then create standard setting. They create the mechanisms for standard setting. And here's where the Research Policy Advisory Board could have a very important role, which then in turn aligns incentives, our personal, institutional, public incentives, creates a fair and efficient administrative process for investigating, for ensuring that good scientific practice is met, and leads to, as it were, very good scientific practice, which in turn produces some kind of behavioral compliance with these norms, institutions, and rules, which leads to really seriously trustworthy science. And I would argue that all of this has to be within a framework of increasing transparency of the sort that you were emphasizing, David, where people in the public really understand what our norms are, what our institutions are, what our rules are, and what our good practices are. Thank you.
All right. Well, I'm going to open up questions for our audience to ask of the speakers in a few minutes, but let me just start with a question for our panel. And let me think about how to phrase this exactly. But one thing that occurs to me, whenever we go out to the public to try to measure, I think measuring competence seems to be a simple thing to measure. You know, either people know what they're doing or they don't know what they're doing, and I think there's little ambiguity in that. But when we're trying to measure this other axis of trustworthiness, or whether people really think that they believe that scientists are acting in their best interests, I can imagine that there might be all sorts of ambiguity in how people might be answering that for the following reason. Most scientists I know, including probably most of the people in this room, their highest allegiance is probably to the truths of nature. That is probably what I think most people would say when they are looking for what they are seeking in the data. It's not necessarily what is in the best interests of society. It's they want what's right, what's true, what does the data really say? And the first thing in their mind is not necessarily what is the best interest of society. They want to get the answer right. And so I could kind of see why people might kind of give them a middling score on trustworthiness, because scientists' number one allegiance isn't, you know, what's best for my neighbor. No, it's what was truth, what was right.
So let me take a stab at that. What we find is that people infer trustworthiness from whether the person is cooperative or competitive in two realms. One is values and the other is resources. And so I think the problems that we pick can reflect those values and those resource allocations. And then so the problems that we pick are useful to people in general or not. And then what you find, might still be motivated by adherence to truth. But it's also true that there are many problems that we pick to work on where we don't know what use they might have to humanity. And that's one of the things that we value in basic science is curiosity-driven science. And so I'm not sure that, I think the academies have a number of projects to make clear the value of basic curiosity-driven science, because that part, I agree with you, is not obvious.
And I want to make a distinction here between scientists and science. So yes, I think the public as a rule, and most of us as scientists, what we really care about is discovery and truth and advancing that. But if we think about science, we care about science as actually ultimately, not necessarily with every study, but ultimately advancing our capacity to live better or to operate better. And the way we do that is not by expecting every scientist to be thinking about that question all the time, but to create a set of institutional arrangements that ensure that our science is more or less moving in that direction, that it's actually serving the public who is largely supporting it and paying for it and meant to be served by it.
And I would add one more thing, which is doing things for the public good, I think, would be very well promoted by more conversation with the public. Because often our research is very curiosity-driven. We really don't know what might be the benefit that this could bring to anybody in any context. But if we talk about what makes us interested in what we're finding out, often people who can, out there in the world, who can figure out what's beneficial for them, are very happy to come and communicate it to you. Yep. So my own work, I'm sure everybody's work here, is useful in areas we never would have dreamed of. And that only comes about by having trying to make sure that you're having a conversation with the public so that they can inform us what's in their interest or how our work can be best applied.
Since I don't see anyone lined up yet, let me go on to one more question. So, Margaret, you raised the topic of the possibility of there being a research advisory board that might span the research enterprise and help deal with this, real or perceived need to signal that there is some oversight body that at least is helping to raise standards everywhere for the integrity of the entire process. A few of the things that I've thought about that it could help with, one might be simply the peer review process. There is no body right now that does spot check audits to for example, check with journals to see whether they have, if they say that they have peer-reviewed a paper, to parachute in and say, in this issue, all of these papers were supposedly peer-reviewed. Please send us the peer reviews for these 2 papers, and we'll make sure that indeed peer review happened. Or setting standards for disclosures of conflicts of interest for funding. Have you thought at all about what might be, whether those would be useful things to do or any other things?
Well, most of my knowledge of this idea comes from reading you. So I should really send this back to you. I see it as really important, though. I mean, I think that kind of thing is great. But I think it's also, and there are a number of other places where those kinds of interventions that are fairly simple would be really helpful. But I also think it's just incredibly important to have some place that we as a society can look that really helps us to understand what the standards are and how they're being set, and that there is someone thinking about whether they're actually being met. So all these, there are lots of, and it's got to evolve. I would not want to see a regulatory body like that or an advisory body like that put into place and its rules set for once and for all. It's got to be constantly responding to the way in which science is evolving.
Right, exactly. So let's start over here.
I got questions.
Please introduce yourself and direct your question to a panelist if you have a specific.
Good morning. My name is V. Shukla, and I'm a plant scientist, and I work at the Bill and Melinda Gates Foundation. Actually, I'd like to ask the entire panel for some additional commentary on the question that you've raised around both values and motivations. And specifically, I'd like to get your perspective on the impact of the Bayh-Dole Act, which allows institutions and individuals to patent and protect federally funded research findings, and the potential for monetization of these findings at the institutional and personal level. Thanks.
Well, I think it creates a potential risk. I mean, so in previous work we had done on trustworthiness of scientists, if you raise the issue that people might be doing something to get more funding, that had a bad effect. And so if you raise the issue that people might be doing something for personal gain from a patent, that would be problematic. One of the things about forming impressions of scientists as a group and scientists as individuals is the framing matters a lot. So what's in people's minds as they're thinking about whether they trust us or not, does have an impact.
All right, let's go over here for the next question.
Jane Richardson, structural biology at Duke University. There was this statement about us only caring about the truth, and we study things for curiosity-driven motives, but you haven't talked about all the evidence there is that that's where the humanitarian and health results come from. And I think one of the things that we should be doing as the Academy is even more work. There has been some, but I think we should really try very hard to document the sources that led to various things that people already value.
So there are a couple projects that.
So we have projects like Research to Reward, which talk about the basic science roots of wonderful things that society truly values today, and other projects like that, the science behind it, that show how our investment in research has led to understanding that we very much value. But clearly, this is a bottomless pit for investment in public understanding. Yeah.
And I would like to see, as well as anecdotes, which are wonderful, some actual numbers. You know, is it just a few cases in the public perception? But I think we could document that it's actually a very large percentage that came from basic science. And if that's true, it would be good to really make it known.
Yeah, I think there are numbers. I think NSF has numbers. Yeah. Let's go.
My name is Leon Rosenberg. I've just retired after a lengthy career in academic research, academic teaching, private industry, and most recently as a high school teacher. And I would like to ask any members of the panel, what do you mean by the phrase, the people? How much influence do the people you survey, based on their educational attainment, gender, color, regarding their level of trustworthiness, our trustworthiness to them?
Question.
At least in our data, it doesn't matter who you ask, because what we ask is, how are scientists, for example, viewed in society? And it turns out that there's a pretty good consensus on how these different groups are viewed on our warmth by competence space. And so it turns out not to matter who you ask, even if people are members of the group themselves. There's very little in-group distortion.
However, I would say, though, that it is a wise question to ask. I would even expand upon it, because not only is it there the people, there is the issue.
Yeah.
And I think anybody who's interested in the issue of trust in science and trying to change the state of affairs has to understand there is always a botany of people who bring different levels of knowledge, different levels of motivation, different types of ideology to any sort of issue. And so an intervention or a thought or a theory that might work for one group of people on one issue might have to be modified or changed over completely for another one. So I think one does want to establish the general case, and we've been talking about the general case here today. It's a very important general case. It's a classic case in terms of trust of individuals and institutions, but to understand that there is a zoology of concerns that one has to deal with if one wants to get into the mix more specifically and more successfully.
And let me just bring in the political scientist point of view here. So part of why we are concerned with the public, whatever we exactly mean by that, is the public votes. And the public, some proportion of the public, their views, their pressure affects legislators who then have consequences like the issue we were just talking about the patent law. And we need to be sure that we get the public's understanding of science and the lawmakers' the decision makers' understanding of science more aligned with what science really is.
So we only have 3 minutes left, so we're going to have to go really fast.
In addition to the question of who are the people, I would ask what is science? I think there's a big difference in my mind anyway between the medical dental professions,
Absolutely.
as mentioned, and basic science. I also regarding the people, wondered about the questions, even the questions we were asked today. There were some ambiguities in my mind in the questioning, and I wonder, and also the language was very high level, and I wondered when you ask even college students, some of the questions seemed to me, the idea of, quote, running counter to seemed very high level. And the third thing is really just the dumbing down of surveys generally. I took a survey.
I think
yes.
this question is more for Kathleen, so maybe
Okay.
you should ask.
Okay, well, the third one is about, dumbing down of surveys. Stanford Healthcare Alliance asked a whole series of questions which were like, do you like your doctor because he or she knows your name? Not, do you like your doctor because he or she seems to know a thing or two, seems to know the field, seems to be competent, seems to be thoughtful. They don't care. So I think surveying is really another part of what we're talking about now. Thank you.
Up to 3 minutes.
Yeah, let's go over here.
John Coffin, Section 44, Tufts University Medical School. I've been increasingly concerned lately about, it's hard to turn on a TV without seeing a theme, particularly in sort of legal thriller shows and things like that, of corruption in science for some reason or another, the expert witness who will say whatever he wants to for a price, the drug company that conceals negative results. These are all very common themes in TV shows and books and so on. And so how much is this affecting the perception of the public, and is there anything we can do about it?
Well, we do have a program here, the Science Entertainment Exchange, which works very hard to get more realistic portrayals of science and science characters in both television shows and in Hollywood. And I think they have had success in a number of series, but nevertheless, you still see that happening despite their best attempts. The meme of the corrupt witness or the mad scientist is still prevalent, and we're still working to counteract that. Over here.
I'm Paula England, a sociologist and new inductee. We have two esteemed social psychologists on the panel. I wonder if they could comment briefly on whether you think there's a crisis of replication and reproducibility in your own subfield, as some are claiming, and what you think could be done about it.
Well, that's a small question.
Yes, and lots.
I think that there is a replicability concern that's been raised across fields of science. If you look at it, it's not just social psychology.
Right.
And I think some helpful things have come of it, that there's, what we're going to talk about, increasing trust in science and solutions, but the movement for open science, and the requirement that your methods get posted, that your data get posted. There's difference of opinion about whether it's a good idea to pre-register your hypotheses or not, but there's been a lot of discussion, and I would say a sea change in the methods.
So,
If I could just say.
And we're going to talk about this some more.
Yeah, I'll just say, and I think we're just in the middle because a lot of new standards of best practices are going to come up from the discussion, sometimes contentious, that's going on now in social psychology and hopefully elsewhere. I'll just put in a plug that I wish institutions would get involved a little bit more.
yep. So if these last two questions are really fast, because otherwise we're cutting into the break. So really fast. No. Okay, all right.
Bruce Alberts. I just wanted to say one thing, that people in this room have control over one thing, and that is how we teach science at universities. And I would be very interested if anybody is doing or has done a study of how, you ask your questions before and after somebody takes an elementary science course at your university, and what if there's any change, because in most introductory science courses, we don't focus on getting the students to really understand how science works, and so this is something that all our members could actually do.
I think exactly the stuff that David talked about would be, the kinds of things.
And I would agree with you. And I actually don't think the issue is science classes per se, but scientific application of scientific knowledge to other areas. I teach a psychology and law class. I know after my class, these students will never see the scientific method again. And so I do teach a lot of scientific methods in the class. The smartest students will write down in evaluations, gee, this is a research methods and law class. This isn't a psychology and law class. And I'd actually think that might be the classes where the action is.
Right. So if I could have the next slide up here as you're going into break. You have one more assignment here, and this is to do on your cell phones, for those of you who brought cell phones in here. If you text the word NAS to this number, 555-888, then you're going to get back a confirmation message. And you can submit a text response to the following question below. We'd like anyone who has a good idea to submit an example of a problem and solution from your own discipline that increased the trustworthiness of research in your discipline, and include your name if you want to be identified. What we're going to do is during the next part of the session, we're going to, Susan and I are going to grab some of the best ideas, and we're going to then post them up at the end of the next panel of great ideas of disciplines that were able to increase the trustworthiness in their discipline through active intervention, and post those up, and your name can be up here in lights if you want it to be, or at least your idea can be. So go ahead and text those good ideas, and we'll share them with everyone, okay? And unfortunately, we can't do them on the clickers, because the clickers, you can't put a text idea in. And then come back in 15 minutes, and we're going to have our next panel, okay? So let's thank our panel here again.
And with that as a predicate, we're going to have a panel that's going to tell us about all the solutions that are in place that are addressing the non-crisis, but the challenges that are facing science. And I'm going to introduce the panelists from here, and then I'm going to join them. They're going to present in order. Peter Bandettini has a PhD in biophysics from the Medical College of Wisconsin, where he led the effort to carry out one of the first successful experiments in functional MRI. In 1999, he was the chief of the section on functional imaging methods at the National Institutes of Health. Recently, he has become the founding director of the Center for Multimodal Neuroimaging at the National Institute of Mental Health. He's also recently completed a 6-year tenure as editor-in-chief of the journal Neuroimage. Would you raise your hand, please, Peter? Jeff Leek is a professor of biostatistics at Johns Hopkins Bloomberg School of Public Health and co-director of the Johns Hopkins Data Science Lab. His research program has focused on the analysis of data from high-throughput genomics and education experiments. He's also published papers on the rate of false discoveries in the biomedical literature and methods for evaluating rates of replication in large-scale replication studies. Would you raise your hand, please? Jeff, thank you. Leonard Freedman is the Chief Science Officer of the Frederick National Laboratory for Cancer Research. He's held leadership positions in basic biomedical research, drug discovery, and science policy in both the private and nonprofit sectors, as well as in academia. In 2012, Dr. Freedman became the founding president of the Global Biological Standards Institute, GBSI. Prior to starting GBSI, Dr. Freedman served as the vice dean for research and professor of biochemistry and molecular biology at the Jefferson Medical College, Thomas Jefferson University. And Veronique Kiermer, I apologize to Veronique because I've gotten her name wrong so many times. Is executive editor of the Public Library of Science, responsible for editorial and content direction and vision for the PLOS suite of journals. Prior to PLOS, Veronique was director of author and reviewer services for Nature Publishing Group, where she oversaw the Nature journal's research integrity and editorial policies. In 2010, she became executive editor NPG, overseeing editorial policies and editorial quality assurance for Nature and the Nature journals. Please join me in welcoming the panel, and they're going to present in serial order. after I walked them the clicker.
Okay. So my talk, I come from an area of brain imaging, so I'll use it in the context of that, but it generalizes to most anything. So as you heard today, there's a self-correcting process that's sort of iterative of the process of science. Essentially, people do experiments, have meeting abstracts, they submit papers to peer review. This is an iterative process. Finally, you have publication. Finally, if there's enough publications, it goes through clinical trials if it's a clinically related research, and then finally implementation. Any one of these steps could be wrong, and any one could be problematic. Even clinical trials have been incorrect. So this is just to reiterate some of the problems. Some of the data are, the experiments are underpowered, data not shared, tools and code aren't shared. There's minimal standards in terms of how to do best practices. And researchers have even a hard time keeping track of their own data, much less trying to pool other people's data. And there's minimal training in study design. And also, within the whole publication process, it's sometimes opaque and sometimes slow. So this iterative process, it would be nice to not only make it more effective, but also to speed it up in some way. There's limited accessibility to papers generally, or there has been, and poor replicability of results for the most part. And tools, details, and data are relatively unavailable, or they have been. So just to summarize the challenges, the reproducibility problem, there's a lack of integration of findings. There's so much data being produced, not much is actually being integrated. Curating data, working with big data sets is becoming a large field. That's still a problem of how to do that best. And also the publication replication process is yes, it's self-correcting, but it's still potentially slow. And so maybe that's why there's some perception of not good self-correcting. So this is a study, recent study in Science on a replicability study. And everything in this, basically, every dot is a study, and the size of the dot is significant to the study and the initial finding. And the green dots are ones that were actually successfully replicated. The reds are not. So about half the data, half of these studies have not been replicated. So that was a little bit eye-opening. And also the integration problem of data is not new. So at NIMH, had a task force. They even, back as far as 1975, said that we're generating all this data in these siloed labs. It needs to be more transparent, and it needs to be more usable. And slowly but surely, the data are becoming more shared. So this is a graph going from 2000 to 2017 on reproducible research practices. Basically, how many labs share their data, put their data into a data pool. And it's slowly growing. You can see about 25% finally are catching on. So what are the solutions? So it's all about incentives, I think. Incentives to create curated, freely accessible, pooled or single set of data sets. Incentives for research to share data and tools, online tools, faster, more transparent data publication process, incentives for replication and pre-registered studies as well. They're less attractive, they're less interesting to a lot of scientists, but they're important. And so how do you make those incentives? Incentives to publish even negative findings. Most journals just reject negative findings out of hand. That's slowly changing. So NIMH has actually also had just recently a strategic plan for research, which they encourage investigators to use a standard set of common data elements, and they expect investigators to share the data in biospecimens. So this has been something sort of this is one incentive. So they have a plan, they encourage strongly intramural researchers and extramural researchers to share their data. There's the NIH Open Data Initiative, and so far, it started in 2018. So far, there's already 82 databases so far. They use this FAIR principle: findable, the data has to be findable, accessible, interoperable, meaning it has to be usable across different platforms, and reusable. Even one-off experiments are potentially usable. I think that it's turning the field, I believe, at least in neuroimaging and other data, is that the data are used for a paper and they can be reanalyzed in so many different ways, and often that's not done. So there's also NIH-funded curated data sets. So these are all funded by the NIH. They're curated by a specific center, and it's growing in number. You know, you have up to 35,000 with the UK Biobank. You also have open data. These are community-recognized repositories, such as you know, I won't go into detail, but there's many that are sort of open for people to put their data into. So as I mentioned, the UK Biobank, that's the largest one I've seen, and it's the most multimodal. It's everything from genome data to brain data, and their goal is ambitious, up to 500,000 individuals. And this is going to be a treasure trove for reanalysis. And also, and you know, obviously people are very excited about this as well. So not only is sharing data important, but sharing code and papers to allow the studies to be more replicable. So there's a lot of work from a sort of a grassroots movement. Russ Poldrack and Talia Coney are just two of the people pushing that in our field of neuroimaging. In data sharing, there's also software tools that are becoming more available online. They're also creating more standards as well. So these people who create these tools and foster data sharing are also getting from the community sort of a set of standards that are constantly updated on how to do the data, how to analyze the data that are generated. And then lastly, publications. It's mentioned bioRxiv, and interestingly, that's one example that's, you know, it's not peer-reviewed, it's commented on after the fact, but it's exploding. It's a sort of a movement that's sort of grassroots as well, that people are becoming much more comfortable putting their novel findings in these preprint servers before they're published, just to get them out there and get them commented on. And it turns out that these papers are actually ended up being more published, more referenced than other papers as well. So lastly, just to summarize, there's a shift in the culture of doing science. It's both top-down, funding mandated, or bottom-up. I think that there's slow changes in the culture of open science. So the NIH is mandating data sharing and pooling. NIH-funded propagation of available curated repositories and tools. The publication culture is changing with open access and available code and data, and pre-registered studies and clinical trials are also becoming more common. So thanks.
Yeah.
Right, so while that's getting set up, I'm a statistician and I feel like I should be here a little bit apologetic. One of the papers that I think led to the crisis narrative you talked about is a paper that was published called Why Most Published Research Findings Are False, which had a statistical argument that described why most research was false. And so I'm going to talk a little bit about the relationship between statistics and trust in science. I talk fast and we have a short time window here, so if you don't follow all these slides, you can find them on my website. So my first, I have 3 points I'd hope to take home. First is we need to settle on a definition of what false is if we're going to talk about crises. And again, I ascribe to the same belief that there's not as much false science as people would say in these crisis narratives. The tools exist to do good science, as it was just very nicely pointed out by Peter, and that a key component of moving forward and really correcting the scientific enterprise is training not just for scientists, but the entire community around data and statistics and what those things mean. So first, what is false in science? You see these sorts of headlines about the crisis narrative, and if you Google for most science is wrong, you'll get 176 million hits on Google, which is a pretty bad sign. But one of the things that you want to ask yourself is, what do we mean by false? So this is a sort of a schematic of a scientific process, all the way from thinking about the question you might ask to making a claim about that population. And when we talk about these terms, we need to be very explicit because every field uses them a little bit differently. The way that I use these means for reproduction of a study means I've done the whole study, I don't collect new data, and I hand the code over to somebody else and they can rerun the code and get the same results. That's called reproducibility in my field. In my field, replication is you recollect data and redo the study. That will introduce natural variation, and sometimes you'll get a different answer, even if you did the study perfectly. And then a false discovery is where you make a claim about the state of nature and that claim turns out to be false. And so when you hear false discoveries or most science is false, you think false discovery, but most of the data we've collected is about replication and reproducibility, which aren't the same thing. We've done some studies of the rate of false discoveries in, say, the medical literature. My colleagues and I used techniques from genomics to try to estimate the false discovery rate. Turned out there was a relatively high true positive rate in the medical literature, according to our estimates. There are other estimates out there that fluctuate a little bit around this, but the false discovery rate is not as high as people would sort of suggest, according to the best research and the best data that we can collect. So the other point I would make very briefly, because Peter said so nicely, is that the tools exist to do the good, open, reproducible, self-correcting science that we would like to see. So you can use R Markdown to write documents that have code embedded in them. You can share your code on GitHub. You can produce these data documents and put them on Figshare and share them with your colleagues. And you can pre-register your studies with things like the Center for Open Science's pre-registration documentation. Many of these tools are tools that were built by scientists in just the last 5 or 6 years in response to this crisis. And it shows very much that scientists are actively trying to address these problems. And so it's exciting that we now have the tools available to actually produce open, replicable, reproducible science. So what's the problem then? So the problem, in my opinion, and the big thing that we need to work on now, and scientists are actively working on, it's a little self-serving because I do a lot of this myself, is training. Training is the solution to the crisis. I just mentioned all of those tools, R Markdown, GitHub, Figshare. How many of you know how to use all of those tools? And so those tools we need to train people how to use. We don't have the clickers out, so I can't get a survey, but that's where the action is. So I have an idea about the way that we can move forward, and you'll have to decide for yourself whether it's a good idea or not when I'm done talking here in a minute. So if you remembered anything from your first statistics class, you'll remember either the letter N or the letter P. N is the sample size. And there's a very good formula for discovering how big a study will be when a scientist runs it on federally funded research dollars. And so the denominator, I don't know if you remember your fractions, but if the denominator gets smaller, the N gets bigger. And you can see that across all different fields right now. In my own field, it used to cost $100 million to sequence a human genome. You can now do it for about $1,000. What does that mean? We've had an explosion of data in our field that's very difficult for people to work with. And that explosion has happened over a very short time frame. In 5 or 10 years ago, you might have 1 or 2 genomes. Now you might have 10,000 or 50,000. And if you're not trained to computationally and statistically handle that kind of data, it's an overwhelming thing to deal with. So there's this other cartoon I like. I don't know how to do statistics, but it doesn't matter because I didn't have data, is maybe a good representation of a lot of fields that had limited data sets and limited access to data, and so didn't need deep statistical and machine learning and computational training. But that's changing over time. A good representation of that is to get into medical school, you need a year of biology, physics, English, and chemistry. It says nothing about statistics or data management. But if you go and look at your average paper in the New England Journal of Medicine and you color code each sentence by what fraction of those sentences include a statistical term, more than 50% of the sentences in your average abstract in New England Journal of Medicine contain a statistical term. That means a medical doctor wanting to read the medical literature and the latest medical research basically has to have a statistics class, otherwise they won't be able to read the papers in their own discipline. This is reflecting itself across all of science right now, and we need to be focused on the fact that we've developed these amazing tools. We have the techniques that have been developed to address this issue. We just need to get them into the hands of the users and democratize statistical and data analysis. So we've developed lots of courses. This represents 3 people in a medical. I often work in the medical area. This represents 3 people. The coder that's analyzing the data and building a machine learning algorithm, the physician that's actually working with the patient, and the patient themselves who's collecting and using that information to make decisions for themselves. We need to train all 3 of these cohorts of people. It can't just be the person coding behind the scenes knows about statistics and data. It's now important for all of us to understand that, and that will help address the difficulties that people have interpreting the narrative that science is in crisis, when in reality there are very nuanced statistical issues that are going on that merit deeper discussion. So training is the solution to the crisis. My colleagues and I teach these classes online, massive online open classes, but everyone is starting to teach these classes at their own universities. And to the extent that we can integrate statistical data analysis and data management strategies into training programs across the scientific discipline, I think we have a real opportunity to take the learnings that we've already developed and that scientists have already spent a huge amount of effort producing and make them useful for everybody. So with that, I'll turn it over. Thank you very much for your attention.
Hi, good morning. It's an honor to be here. I'm going to tell you a little bit about some work that was taking place over the last 5 years at the Global Biological Standards Institute, which I led as a nonprofit based in Washington, D.C. that was focused on advocating for a broader role of standards in biomedical research. And as part of that work, we about 4 years ago published a white paper called The Case for Standards in Life Science Research. As part of that work, we deconstructed, if you will, many of the drivers based on surveys of academics, pharma folks, funders, journal editors, of what the 10 major drivers for reproducibility would be in focusing on biomedical research. You can see that in the middle column there, incomplete protocol reporting, reagent variability, et cetera. One interesting thing I want to say about this is that scientific misconduct, which Kathleen talked about and we hear a lot about, is actually quite rare compared to some of these other drivers. I want to really focus on one example, like Jeff focused on statistics. I want to focus on how reagent variability and the lack of validation of biological reagents can contribute to reproducibility. And in particular, I want to talk about misidentification of cell lines that are used in many, many laboratory experiments. And given that I only have a very short amount of time, we can just reduce it down to this slide. The drivers for misidentified and unauthenticated cells are cross-contamination of those cell lines, mislabeling, even genetic drift that occurs, particularly in cultured immortalized cancer cell lines. And that's gotten a lot of attention, and many examples have been published in the literature and even in the lay literature. These are just two I selected from the last couple of years. One last year in PLOS One, which is an example of cross-contamination. This is a paper that I think cleverly entitled "The Ghosts of Gila: How Cell Line Misidentification Contaminates the Scientific Literature." And in that paper, the authors found that over 32,000 articles reporting on research used misidentified cells. But what was even more sobering was that they were in turn referenced by 500,000 other papers. And then in Nature last year, Todd Golub's lab published a very, very detailed demonstration of how there's a genetic drift, if you will, can have a very profound effect on the drug response in cancer cell lines that are being screened for various inhibitors of cell growth. What about specifically cell misidentification, which is sort of bad news, good news here? It appears that anywhere from 15 to 36% of cell cultures in circulation today are misidentified. And there's actually a website called that's run by this organization called ICLAC, the International Cell Line Authentication Curation. And they have identified in this website over 500 cell lines that have been established to be misidentified. Many of them are still being used and still in circulation. And the other issue is that many researchers still simply don't authenticate cells, and there's a very considerable cost to that, which I'm going to show you. We carried out a survey in 2015. We published it in Biotechniques. This was a survey of close to 500 biologists, people in the lab who were using cells and cell lines every day. And to cull it down to one, I think, very revealing question and result, the question was, how frequently do you perform the following confirmation of species-related quality controls? And there are a number of them, including DNA sequencing, DNA fingerprinting, et cetera. And in each case, you can see the gray in the middle. The answer was never, 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 which is really kind of depressing and sobering, especially because there actually is one of the rare biological standards that exists, an actual ANSI ISO standard, is STR profiling or DNA fingerprinting. This was developed in 2011 by an international group of academics and as well as ATCC, the Cell Repository. And it is actually now included in many journal guidelines and in NIH grant applications, but we can talk about perhaps in the discussion whether or not it should be absolutely required. And there's also a pretty profound financial impact to how, on the one hand, the misidentification of cell lines is a big cost to the biological community, and how this easy fix can close that gap. This is a back of the envelope calculation we did where in 2015 NIH funded close to $4 billion worth of grants that involved cell lines. If we apply that 15 to 36% misidentification rate of cell lines in general, that's a cost of about $1.3 billion. If we reduced that 15 to 36%, not eliminate, because that's obviously not realistic, but reduced it to 5 to 10%, we could actually lower that cost and save over $1 billion a year just in reducing the number of misidentified cell lines in circulation. So I think that we've sort of alluded to how we can try to incentivize the scientific community. There's the carrot and the stick approach, and I think Veronique will discuss how journals can be a big factor here as well. The NIH in 2015 introduced a whole series of guidelines in a rigor and reproducibility initiative, including the description in grant applications of authenticating biological reagents. So that is progress, but I think we have a long way to go. And then Jeff talked about specifically how training is important, and we were actually the recipient of an R25 training grant from the NIH to generate an interactive video training module to actually teach people both the importance of good cell practice and how to actually authenticate cells, and that's available on NIH's clearinghouse for training modules. I think a broader role really there's a huge opportunity here for a broader role for training the upcoming generation of scientists on the importance of validating biological reagents. And this is really an example of some low-hanging fruit here. We can also think about how important antibody validation is. Anybody who's used research antibodies knows what a complete mess that is, but in comparison, authenticating cell lines with a known standard is low-hanging fruit. Thank you.
Hello, I'm Veronique Kiermer. I work for PLOS, the Public Library of Science, and I'm here to represent the perspective of journals and what journals can do. Journals have a responsibility of stewardship of the scientific record. We're expected to ensure that the scientific methods, as well as the discipline-specific solutions that are developed in the laboratories, are actually applied in the research that is published. You've heard a few examples today of these discipline-specific solutions that are being developed and very actively over the past 10 years. There are many more than that. And they all fall under what I would call when they are applied, I think they are signaling rigor in science, and that would fall under the competence element of trust that we discussed this morning. We're also concerned about another aspect of trust, which is integrity. And breaches in integrity, which happen when norms of the fields are not being adhered to, can have a very damaging effect. And even if they don't compromise the quality of the results. So it's very important for us to focus both on rigor and integrity. There's another element of trust, obviously, which is fraud. And I want to stress here, fraud can be a breach in any of these categories. And I want to stress here that in my experience, at least, the cases of fraud are very rare. And so when we are devising solutions, we have to take fraud into consideration. They can be very damaging, these cases, and they can never be ignored. But we need to think of solutions in a broader way than just focusing on trust. Now, the challenge is to look at rigor and integrity that journals face are first and foremost the fact that these issues are incredibly complex and the variety of issues that happens. And the second aspect is that as the scientific literature is growing, we have to develop the ability to do that at scale consistently. At the Public Library of Sciences, we publish several multidisciplinary journals, including one with a really high throughput. And so we use a three-pronged approach to look at rigor and integrity. First, we insist on transparency, because without transparency, you cannot even evaluate rigor and integrity, and we signal our requirements to transparency through our editorial policies. The second approach is that we rely on multiple actors to effect checks at different stages in the process. And finally, we try to promote open science with the premise that by bringing more transparency to the research process itself, we are facilitating reviewing by peers both before and after peer review, and it's very important to after publication, and it's very important to remember that peer review doesn't stop with publication. Here is a schematic of how we use these different actors in the system. In most of our journals, staff, editors on staff actually effect a battery of checks before a paper is even sent out to peer review. They look at compliance with journal policies and ethics. They look for flaw in study design, major non-adherence to discipline norms, ensure that relevant competing interests are being disclosed, and that there is no plagiarism. Obviously, editorial decisions are taken by or in consultation with practicing scientists, and these are people like you who know the norms of their field and understand the nuances of their norms and can marry that understanding with the understanding of journal policies. And obviously, these decisions are being informed by expert peer reviewers. It's that combination of different actors that actually design a very rigorous process. And even on our most inclusive journal, PLOS One, our acceptance rate is only of 50% based on this process. The process is rigorous, but it has two drawbacks. The first one is that it's still only a handful of experts looking at each paper before the paper is published. And the second drawback is that it can take time. This can be particularly a problem when the dissemination of results is actually being held up not necessarily by concerns around rigor and integrity, but around more subjective assessment of importance of a result, as can be the case in our more selective journals. And so to address these drawbacks, our very biomedically oriented PLOS journals I've adopted a solution that was designed by physicists in the 1990s. Never too late to learn, and that is the publication of preprints. So we encourage authors to submit a preprint before they submit their article, and if that hasn't happened, we offer the authors to actually post a preprint on their behalf. We do this after we've operated our initial checks to make sure that we've screened out anything that could potentially have an impact on public health or the environment or have a breach of integrity. We do that in partnership with bioRxiv, which has been mentioned before, and this is one way in which we are trying to make the process more transparent and to bring more eyes on a research paper earlier in the process. So this is one way in which we operate open science. There are other ways. We have editorial policies demanding access to the underpinnings of the conclusions of a paper, in particular data. We have a very stringent data availability policies. Sometimes we demand true policies. Sometimes we try to facilitate the sharing of details, like in the partnership we have with an open protocols platform that allows authors to have much richer method sections because they can include step-by-step procedures. It's also about looking at the publishing process itself and whether it can be adapted better to actually serve the scientific process. And we are currently experimenting with registered reports in collaboration with a couple of granting agencies in which the peer review occurs very early in the process at the time of grant application. And then finally, it's about applying that transparency to our own process. And we're just about to launch the option for authors to publish the peer review of their articles alongside the article. So we're seeing open science as a way, as an enabling strategy, because by shedding more light on the process by which results are obtained and published, we actually are allowing the broader community to better interpret these results. What we're seeing in our experience is that the community is very willing to try these new approaches and to go for open science. What's going to be very determinant is that we are able to signal to the public and the community that these practices are being taken and to create incentive to actually promote open science. I'll leave it at this.
Thank you. Please come to the microphone if you have a question or a comment. And as people determine whether they'd like to come to the microphone, I would like to ask a question that has troubled me a great deal, and it is about a study that, Jeff, you referred to, that was translated to the press as "Most Scientific Findings Are Wrong." If you could please retitle that article for us, what would it say?
I would say a simulation study about the way that science might work suggests that there's a way in which most science could be false.
At least that would be an unquotable headline, and hence less likely to be prompting overgeneralization.
It was a simulation study where there were some choices that were made about parameters that when you make those choices in a certain way, you can tune them to make science look one way or the other.
And Veronique, I know the journal that published this, I believe, was in your suite of journals. Could you talk to us about any thoughts in retrospect about the titling of that essay?
I think this title was definitely trying to get attention. We must say that this was in 2005, when actually these questions around statistics and reproducibility were not really discussed a lot. And so I think that the context in which this paper was published is important to remember. Should it be published today, it would have a different title, and I would refer you to an update that actually John Ioannidis, the author of this paper, did quite recently to really highlight all the nuances and all the measures that are being taken by the scientific community to address that, and the importance of scientific evidence in multiple decision-making processes.
When we looked at those...
One question from each side, and then the buses need to go.
Okay, go.
Okay, thank you very much. I'm Günther Wagner from Yale University. It's important, I think, to recognize that there is a role to be played by the national academies in this problem of education. As long as the medical schools don't require statistics, it will not be taught to pre-meds. I can tell you that I'm coming from a faculty meeting on Friday where our faculty was pushed back in our request to actually make it mandatory because first, it's not required by the medical schools for admission. The second is students don't like it, and therefore, in the marketplace for competition for students, we would lose out. So we are told we cannot require it.
Thank you for that important point.
Thank you very much. Has to be on the national matter.
Thank you.
I think Susan Harrison, University of California, Davis.
I think this question may go a little bit to the substance of the paper you were just referring to a couple minutes ago. What do you think about this idea that there is this kind of hardwired rate of false positive results, and that when you combine that with intense pressure on a lot of people to publish only flashy positive results, you're going to have this endemic problem, whether you call it a crisis or not? But how do you root out that problem? I don't see that quite being addressed entirely by the solutions that you've talked about.
Good question. I think that one's for Jeff.
Well, I think it might be actually more appropriate for the editor of a journal.
I actually think that solutions exist to actually publish. You have a number of journals now who actually welcome negative results and hypothesis verifications. And so I think that the solutions to actually make these results available and address publication bias are there. I think what's missing is the incentives to do that.
Well, yeah, the institutional rewards need
exactly,
to be there. Yeah.
Exactly. So institutional rewards to actually publish negative results is a very important aspect.
And with encouraging everyone to put those institutional rewards in place, please join me in thanking the panel.
All right, thank you very much. We're just going to flash the results of the suggestions that people sent in, and then the buses will be ready outside to take you all to your section meetings. And thank you all very much. The reason we did this, just to let you all know, is that I think this issue of the trustworthiness of science is something that the Academy has to take very seriously. We discussed it extensively at our strategic planning meeting, and exactly what should be the Academy's role in this is something that I think we have to discuss as an organization. So I hope you all took some takeaway messages from this discussion this morning, and will think about what should be the role of the Academy in ensuring the trustworthiness of science, because as leaders of the community, this is something that we have to show our leadership in ensuring that the United States, the public, and our elected leaders can trust science. So thank you all very much.